This video is part of a course on digital food physics and engineering. So where does digital food physics and engineering fit? It is really part of digital food manufacturing that includes many things. I have picked up 4 such items, and they are computer-aided engineering, digital twins, smart appliances, and systems approach. The reason I picked them is that they are, of course, very critical and in the forefront, but models of the kind that this course is about play a very important role or can play an extremely important role in this process. So we will spend a little time on each one of these, and these will be of a survey nature. So the course itself is more of a fundamental nature, but these are just introductory pieces that are introducing the concepts where the modeling would eventually fit. And so these themselves are more of a survey nature. So with that, we get started. So first, some characteristics of food in this context. Food really has unique challenges, and let's look at some of those challenges. For example, structurally, it's complex, and its relationship to sensory, from its composition and its relationship to sensory, is very complex. It's not like we have nice little relationships available for these that we can use to build model. Then there is also high variability here. And the next thing is there are massive changes during processing. So think of starting from a dough into the bread, how much changes, how much change happens in the thermophysical properties of food. Then another thing is it's not like we have already resolved these thermophysical properties and the relationship between the start of a process and the end state. The entire process has been resolved. We have not, because these processes are very complex and there are limited engineering studies. Then the next thing is that the food processes often involve multi-physics. So there's fluid flow and heat transfer, and it could have electromagnetics. It can very well have solid mechanics, because every time you process, its size changes, because if it loses water, it shrinks and so on. So there is multi-physics, and multi-physics is challenging. Another aspect is food. Understanding food, it requires multidisciplinary human resources. For example, we need chemistry knowledge, we need microbiology, we need material science, and so on. So that also makes things complex. And finally, the raw material cost is not as much as many other man-made materials, and so there is less incentive in understanding these in the most precise way and building a model. We're going to start with computer-aided engineering, which is one of the 4 items that we're going to talk under this digital food manufacturing. I'm going to now define these 3 terms that we use, sometimes even interchangeably, but maybe it's a good idea to try to define it a little bit. So these are
computer-aided design, that's this one, computer-aided engineering, and computer-aided manufacturing. Computer-aided design is talking just about geometry. So we take the simplest situation like this canned food, and we draw a cylinder before we do any analysis. So that's drawing the geometry, and this is what we would call computer aided design. Of course, it's a lot more complicated situations. That's why it's a field by itself of getting the geometry, but it's getting the geometry that is computer aided design. Computer aided engineering, on the other hand, is doing analysis with the geometry. So in this case, let's say we're heating this can, and so you can see these profiles that show, let's say, how temperature changes from the surface to the center. So we can do all kinds of analysis, how the bacterial concentration changes. All of these analysis are on top of the geometry. And so that's what we typically mean by computer aided engineering. Then the next level is computer aided manufacturing. And here we have it can be much broader, a lot more things going on. It can include computer aided engineering, but it is normally in relation to automation or operation of manufacturing processes. So for example, in this patent from some time ago, it's talking about cans being fed to this canner and then taken out here, and this canning process is to be controlled by a controller which could be driven by a host computer. Now as time goes on, we could also add some computer aided engineering to it, but you can see it's in a bigger context of the manufacturing that we mean by computer aided manufacturing. So here we see an example of computer aided engineering. So in this case, it's a model showing simulations of microwave drawing of a cube of potato. And the first picture shows the pressure inside the cube, and it's pulsating because the microwaves are going on and off. The second one is showing temperature, third one is showing moisture, but you also see as it loses moisture it shrinks, so you can see the geometry shrinking. And so again, you see this as a very complete picture of the process that would be very hard to get just experimentally. And this kind of physics-based model are the building blocks of computer-aided engineering tools. Next, we'll talk about digital twins as part of the digital food manufacturing. But rather than me trying to explain to you, here is a nice video. And to play the video, simply play on this YouTube button and watch the complete video. Now I will try to illustrate the idea of digital twin, taking meat cooking as an example. So here is the physical process of meat cooking, and here is a simulation of a model for meat cooking, showing how temperatures or bacterial concentration changes during cooking. But the model behind this simulation is not the same as a digital twin. Digital twin is more than a model. A digital twin has to be associated with and continually connected to an object, a physical object like this one. So how does it do that? It, the digital uh, twin has to have the ability to evolve as reality changes, and it has to be able to make predictions with high degree of confidence when the reality changes. How does it do that? So for example, we can have sensors that sense the actual temperature, and we can have user input, like if there is flipping. Put all this information in a database, so the database can store things like different model parameters or even different models, like a data-driven model and a mechanistic model, and different heuristics and rules governing quality and so on. So with that, it makes the predictions, and those predictions provide feedback to actually manipulate the meat cooking process. So this is how it completes the loop. This model and the database together is what we would refer to as the digital twin. And so it's connected to a physical process, and plus it has the model and the other pieces. Eh, So zooming out, this was only the cooking process. Zooming out in a meat, uh, in terms of the life cycle of the meat, starting from the slaughterhouse all the way to consumption, there are many processes that it goes through, like storage, like freezing. And we can think of building a digital twin for all of them, or put all of that material inside one big digital twin of the entire process. That's kind of the idea. And then the digital twin would be able to give all kinds of information as it receives input in terms of how the actual conditions are changing in any one of these processes, like transportation. If the conditions change during transportation, what is the impact of that? So this it can do in real time in a realistic way. That's the idea of the digital twin. Here I take the liberty to show you something from the literature. It is a conceptual model of such a digital twin from my Belgian colleagues. It is one of the earliest, if not the earliest, implementations of this concept for a fruit production or supply chain. I would like you to see the parallel of this one with the previous slide. You have multiple unit operations, like these are different unit operations in the life of fruit production and consumption. For any of these unit operations, like storage, like this one, they have models that relate the input to the output. And there are many details of the model, as you can see here, many details, and it's very rich in terms of models that can be different scales. And but we're not getting into the modeling details. I want you to see the big picture. The model is a virtual representation of the physical process of what is going on in the apple during storage. It also has various related data. So that data, for example, can be real-time sensing how the storage temperature is changing. together the model and this kind of data and the feedback possibility to to the process together, you make it a digital twin of the real process. The real process meaning this production or supply chain or the unit operation of storage. Here is the quote defining the usefulness of digital twins. So digital twins are of most use when an object is changing over time. And of course, you can expect foods change over time, whether it's processing, storage, and so on, thus making the initial model of the object invalid. So if we have models for processing and the processing conditions change, then the initial model is invalid and we have to keep updating. And when measurement data that can be correlated with change can be captured. So if you're doing meat processing, then how does the boundary temperature change? And then I am going to use that boundary temperature in the model to get more realistic simulation. So those are the basic parts of a digital twin. Another area where models can be useful in the context of digital food manufacturing is smart appliances. And we see them all the time when you have an oven at home that has these buttons for different types of food and so on. Um, did you ever wonder how they do this? They have some sort of a model, uh, can be very simple for different types of heating that they found mostly from experiment, and these are built into these smart appliances. So I happen to pick these combination ovens that we're quite familiar with, and these combination ovens where modes of heating like infrared, like halogen, uh, hot air, they can be combined to produce a certain quality or certain desired attribute like uniform heating, for example. How do I combine these different modes of heating? Their models can be quite useful, and I'll show an example. The concept of a digital twin, as we discussed earlier, can be implemented inside such a smart oven as the ultimate smart cooking machine. So let's look at an example. For example, in one of those microwave combination ovens, let's say our goal is just to reheat to this temperature, let's say 40 degrees. I just want to reach there. So what power level should we use? Of course, if we use a high power, we can get there faster, but is that the best? So power level is, it turns out, it's a sort of a compromise between how fast we heat and how uniform. And so what you see here is temperature versus time at different power levels. And so in any one of these, the bottom part, 60 seconds, is the total cycle time, and the top part, 10 seconds, is how long it is on. So this one is on 10 seconds of the 60 seconds, whereas this one, the top one, is 60 out of 60, meaning it is on all the time. So of course it heats the fastest. Now let's look at the non-uniformity information. So in non-uniformity, it first reduces because other places get heated, so the temperature differential inside can go down initially, but as some places keep getting more energy absorbed from microwaves, so they keep getting hotter, so eventually again the non-uniformity rises. And so if we look at, let's say, the fastest heating, the non-uniformity never goes below this level. So in general, this fast heating is going to be the most non-uniform. That's the general trend. And so for slow heating, on the other hand, you can go to very low level of non-uniformity. So such information can be programmed inside a smart oven, and it can thereby use this kind of model-based information automatically, and and that's the built-in smartness that we are talking about. In other words, models are likely playing a. Finally, in this last part of how models can play an important role in digital food manufacturing, I want to talk a little bit about systems approach. We can think of the systems approach to be, for now, the same kinds of ideas that we have been talking about of modeling, but at a higher scale or multi-scale. For example, we could think of combining many aspects of food processing system. Food manufacturing encompasses a procurement, processing, distribution, storage, and consumption. Another way we can look at is food uh, has different aspects, and that is continually changed, starting from raw material all the way to what's available during packaging and distribution and eventually consumption. So I want you to see that as food goes through these various stages, there are information available or can be available of two kinds. One is just databases and other is relationships. So let's look at what we're talking about. So let's say food composition and structure. So we have large databases of food composition and how it changes with various factors, and possibly even including how it is grown. So that's a food composition database. Then there are models and empirical information that relates the composition and structure of these food uh, materials to the raw material properties. What kind of properties? Like thermophysical properties. So either we have property databases or we have relationships that can predict a composition and structure to material properties. Not everything is already available. Then the next thing, from raw material we go to processed material, and so we have mechanistic process models. So in this case, it's there are many models in the literature that can predict the properties of the processed material from the raw material. So in this case, it could be collection of models. Then as or during processing, we have energy use information, and energy use can be very varied, depending on a number of factors. So we have this energy use database. Then likewise, the waste waste generated databases, and then of course during consumption, for consumption we have food safety databases, food risk databases, and life cycle analysis databases. Plus of course how much food is consumed, so we have also consumption databases. And so there's also changes during this packaging and distribution, and we have this kind of kinetics or shelf life databases. All of these, both the data, and sometimes it can be big data, but lots of data plus models like this one or like this one, process models, they all can be put together in a system level understanding and optimization using what is now beginning to be developed for food is systems approach. And why do we do that? For decision making by industry and public planners. This can be at an industry scale or it can be population scale. So this is one of the forefronts of digital food, and you can see how models of the kind that we would develop are a significant part of this. To summarize, digital food manufacturing involves many aspects, and we covered four of these. And these are computer aided engineering, digital twins, smart appliances, and systems approach. And the point we made is all of these can utilize, these are all important elements of manufacturing, and they will become more important in the years to come, but they require models. So we will spend most of our time in this course on building these models.